As a director of research at QuantLase Research and Development Center, my perspective is that the first industry to experience a meaningful quantum advantage will likely not to be general computing, but sector where quantum effect naturally map into the problem itself. The strongest early candidates are quantum secure communication, material and direct discovery, precision sensing, optimization driven industry such as finance, logistic and energy system. So quantum compute, quantum key distribution and quantum randomness technology are early approaching practical development because they directly exploit the physics of light for secure information exchange. Similarly, the quantum sensing may deliver early impact through ultra-high sensitivity measurement beyond classical limit. For large-scale computational advantage, I believed hybrid quantum photonics infrastructure will emerge first. Rather than replacing classical system, quantum processor will work alongside photonic intelligence platforms such as PIPU. PIPU is the Photonic Intelligence Processing Unit, where AI acceleration, anomaly detections, and data-driven inference occurs through photonic dynamics, while quantum hardware handles selected optimization, error syndrome analysis, and state space exploration problems. In finance, for example, portfolio optimization, risk mapping, and market anomaly detections could become early demonstration areas. In quantum computing itself, error syndrome detection and fault-tolerant architecture may represent one of the earliest high-value applications because scalability depends more on stability than simply increasing qubit count. The future quantum advantage will therefore not arrive as a single breakthrough machine. It will emerge through an ecosystem where quantum technology, photonic intelligence, AI, and specialized hardware operate together to solve a real industry problem with higher efficiency, lower energy consumption, and greater computational capability. So this is precisely the direction we are exploring at QuantLase Lab, translating deep physics. So as far as my understanding is concerned, I see AI, high performance computing, and quantum technology not as a separate domain, but as a layer of future computational ecosystem that will gradually converge into a unified intelligence infrastructure. AI brings learning and pattern extraction. HPC provides large-scale numerical processing, simulation capability, while quantum technology introduces a fundamentally new mechanism for optimization, state exploration, sensing, and secure information processing. The convergence will likely happen through specialized hardware rather than through one universal machine. Classical HPC system will continue to provide the backbone for large simulation and data handling. AI engine will manage adaptive learning and inference, while quantum processor will be reserved for selected problems such as combinatorial optimization, molecular modeling, cryptography, and fault-tolerant quantum operation. The missing bridge in my view is photonic intelligence. Platforms such as PIPU, Photonic Intelligence Processing Unit, can operate as an intermediate physical layer, accelerating AI workload through photonic matrix operation, reducing energy consumption, and supporting real-time data processing for next-generation data center. Technically, the future architecture may look like this: electronic HPC for orchestration and memory management, photonic processor for ultra-fast AI training and inference, and quantum subsystem for optimization and uncertainty-driven computation. In parallel, quantum sensing, QKD, QRNG, and error syndrome detection will strengthen reliability and secure communication across the infrastructures. The most important shift is conceptual. Computation will move from purely algorithm-driven system towards physics-driven intelligence, where learning, optimization, sensing, energy detection directly from engineered physical processes. The convergence of AI, HPC, and quantum and photonic will therefore create not only faster computer, but entirely new computational paradigm capable of addressing problems that are currently limited by energy scalability and complexity. At QRDC, this is the long-term vision we are actively pursuing through photonic intelligence and quantum-enabled technology. I would say the biggest challenge for quantum is not funding, talent, adoption, or technology individually. It is the integration of all four into a scalable ecosystem. However, technically the most critical barrier remains technology maturity and stability. Increasing qubit number alone does not guarantee performance because noise, decoherence, crosstalk, error accumulation, and fault tolerance become increasingly difficult as a system scale. Funding can accelerate development, talent can drive innovation, and adoption will follow clear value creation. But without stable and manufacturable quantum hardware, the ecosystem cannot mature. The next breakthrough will come from hybrid approaches, combining quantum technology with photonic system, AI, advanced error detection, and specialized hardware architecture that make quantum system reliable, scalable, and deployable in real-world application. At QRDC, we see this convergence as essential for moving quantum technology from laboratory demonstration to industrial impact. Being a quantum seeker, my quantum heroes are not defined by a single person, but by the pioneer who transformed curiosity into physical reality. I deeply admire Max Planck for opening the quantum world, Erwin Schrödinger for giving us the language of quantum states, and Richard Feynman for envisioning computation through nature itself. But if I must choose one guiding inspiration, it would be Feynman, because he challenged us to stop forcing nature into classical thinking and instead let physics become computation. That philosophy strongly resonates with our work at QRDC, where photonic intelligence and quantum-enabled system aim to translate the language of light into real-world technology.